Welcome to the next lesson in the topic, the particle model of matter. Today we're going to focus on a concept called specific latent heat. So, the very first thing we're going to look at today is a definition of what we mean by specific latent heat. So, we're going to define it as the following. We're going to say it's the amount of energy required to change the state of 1 kilogram of the substance with no temperature change. So, it's usually a 2-mark question, and we've got to emphasize this part, the no temperature change. And we know we also have to emphasize the change of state. So 2 important parts of that. We said in a previous video that as it is changing state, the energy is being used to break up the bonds between the particles to separate them. The energy is being used to break bonds between particles. Now, to emphasize this, we can look at a key graph. And on the y-axis, we're going to have temperature in degrees Celsius. And on the x-axis, we're going to have time measured in seconds. Now, at the very start here, from the origin of 0, 0 to the red cross, we know that the substance is increasing in temperature. Now, when we get to this part, between the red cross and the green cross, we know the substance is changing state. And we know that's happening because there is no temperature change. Well, actually, at this moment in time, the process is melting. And then our substance heats up again, and we get to this point, which is a horizontal line, which is going to be boiling. Now, when we talk about specific latent heat, we're focused on these 2 parts here. However, they're given specific names. When it is melting, we call it specific latent heat of fusion. And when it is boiling, we call it specific latent heat of vaporization. So when it's melting, we've got specific latent heat of fusion. When it is boiling, we've got specific latent heat of vaporization. So these 2 parts are concerned with specific latent heat. These 2 parts, which I'm just going to call X, is concerned with specific heat capacity, which hopefully you've done by this point when you get to specific latent heat. And we know we're concerned with specific heat capacity here because there is a temperature change. And we know that that's concerned with that. Now, specific latent heat has got a nice little equation. And the equation here is E equals M times L. And you're given this equation, so there's no need to remember it. We know that E is going to represent energy measured in joules. M is going to represent mass, and that's going to be measured in kilograms. L is going to represent either the specific latent heat of fusion or vaporization. And again, to work out a unit, we're going to do some rearranging. So just to find L, we've got E divided by M equals L. That means we've got joules divided by kilograms. So joules divided by kilograms, so joules per kilogram for the units for specific latent heat. Now, the values you'll get given are different for fusion and vaporization. So read the information they've given you. You don't need to remember any specific values, but make sure you know they are different. Now, we're going to have a look at 2 examples for this. So, example number 1. We've got some ethanol. And it takes 8,400 360 joules of energy to change the state from a liquid to a gas of this ethanol. And the ethanol we've got a mass of 10 grams. Well, the first thing I'm going to do is I'm going to make sure that we're in SI units. Well, we've got joules for energy, but we know that mass needs to change to kilograms. So what we're going to do is we're going to do 10 grams divided by 1,000, which means you've got 0.01 kilograms. And now we can use our formula. So we're going to use E equals M times L. We're then going to substitute in because that's what AQA wants us to do first of all. So 8460 equals 0.01 times L. Rearrange for L, 8460 divided by 0.01, and that will give us an answer for L. We're going to have a focus on another example. This time we've put an immersion heater in some ice and we're going to melt this ice. So we're going to have a look at specific latent heat of fusion. And this heater is labelled with a power of 50 watts. And it takes actually 5 minutes to melt this ice. So we're just focusing on the state change. So we're going to assume no temperature change. And we know that the latent heat of fusion of water, so I'm just going to denote it with an F, is 334,000 joules per kilogram. And the question asks us, it wants us to calculate how much ice is melted. So we're just going to have a question mark next to our M. And we know, so we've got a specific latent heat question, and we know we can use the formula E equals M times L. We've got an issue. We haven't got an energy. We've only got one known quantity. Well, this is a higher level question because you're going to join equations together. So it's two-step. You effectively need to use one equation to find E, then you're going to use that E to find M. Or we can just join them together, but I'm going to show you both ways. So how does power relate with time? Because we've got M and we've got an L, so P and T must be related. Well, actually, we know that power is a rate of energy transferred, so that means power equals energy transferred over time. So we can do P times T equals E. Or if we're going to use the AQA method, we can substitute in. So we've got 50 equals E divided by, now can I use 5? No, I can't because it has to be in seconds. So we've got 5 times 60, which is equivalent to E over 300. And then we could do 50 times 300, and that would give us 15,000 joules. Well, now we've got an energy, we can do 15,000 equals M times 334,000. Rearrange for M, so we've now got 15,000 divided by 334,000. And that will give you an answer of 0.045 kilograms. And that's fine. That's a really long way of doing it. Or, because we know that E equals P times T, we can substitute it in. So E represents P times T. So we could actually do P times T equals M times L, of joining it together. We can then substitute in our numbers. So this time we've got 50 times 300 equals M times 334,000. Then you can rearrange for M. So now you've got 50 times 300 Make sure you put brackets around it. Divided by 334,000, and that again will give you 0.45 kilograms. So you can do either method. Some students prefer this two-step calculation in terms of working out one value and then subbing it into your next equation. Some people realise that you can just make them to get bring the equations together and then work it out as one. It's really up to you how you do that.